In this course, you will learn about the principles and methods of LCD backlight unit. The objective of this course is to introduce you to the principle and methods of the conventional and new LCD backlighting techniques. Each LCD or LED TV panel needs a backlight. LCD or LED TVs use CCFL or LEDs as a source of backlight. These backlight creates the light that allows the LCD or LED to create an image. However, there are multiple ways these backlights can be arranged, and that arrangement can have a dramatic effect on picture quality. In the past, we could only backlight the LCD panel with a constant light intensity CCF lamp, also known as cold cathode fluorescent lamp. LED or LCD TV using LED arrays can dim the backlight rapidly for optimal display of video content. In the upper example, we see the old situation. One backlight unit brightens the whole screen at a high and constant intensity. The LCD pixels do all the work by window shading. Light intensity is modulated between maximum and minimum by each subpixel. In the lower example, we see how the various LED blocks of the backlight unit are modulated to produce light as desired for the picture. In the white areas, the LEDs may reach their highest brightness. The darker areas require only a little backlight, so the LEDs in these areas are dimmed or even off. As a result, the contrast of the image has increased a lot. The list with the thumbs up summarizes the advantages that comes with local backlight dimming. The scanning feature mentioned in the last bullet is used with direct backlit panels and will be explained in the following slides. We distinguish two main methods of backlight dimming. Please remember that we only talk now about LED backlight. CCFL backlight does not allow any dimming except by hand via the menu and is not discussed here. Global dimming means that we can reduce the backlight but only as a whole screen. The brightness can vary per each new frame. So when there is darkness seen in a movie, the backlight will be dimmed during a number of frames. Local dimming means that we create bright and dark areas on the screen simultaneously. In the dark areas of the picture, the backlight is reduced, while in bright areas of the picture, the backlight may go to full maximum. The LED backlight is made up of thousands of small LEDs. Dimming is done by controlling the brightness of small groups of LEDs called LED blocks. These blocks are working independently. Each block sits behind one segment of the screen. The TV calculates how much light each LED block must produce to display the segment correctly. Because we can dim or even turn the LED off, we can display much deeper dark segments than with old constant backlight that constantly runs at full intensity. Let us talk more about LED backlight. Since majority of the manufacturers are not using CCFL type backlight, here you can see the most common type of LED backlight. Out of these, LG mostly uses ALEF in the premium models of our television, whereas in case of basic models of LED TVs, edge LED backlights are commonly used. Before we go into LEDs, Let's look first at the conventional LCD backlighting method that uses fluorescent tubes. These fluorescent tubes are similar to the tubes that are mounted to your office ceiling, but the tubes for a LCD are much thinner and shorter. Fluorescent tubes gives a pretty good amount of light compared with the old incandescent lamps that we have been using for over 100 years and will be phased out in the near future. To get the fluorescent tube started and working, you need a special circuit. So the LCD backlight fluorescent tube require an inverter circuit. This circuit generates a high voltage to ignite the tube and low voltage to keep it working. The circuit also can dim the light intensity. It is important to remember that with fluorescent tubes, you can only light up the whole screen after switching on the TV or monitor set. Dimming is possible but with limitations. The LED is a solid-state lamp. It is a compact chip that converts electrical energy into light like a normal incandescent lamp but without producing a lot of heat. The old incandescent lamp converts only a few percentage of its electrical power into light. LEDs are around 10 times better and will further improve performance. The LED chip is very small, mostly less than 1 millimeter square, and is actually a diode that conducts the current only in one direction. The light output is dependent on this current. We control the current carefully by a special electronic circuit because there is not a filament that wears out and can break. The LED is very robust. It has extremely long lifetime as well. The high brightness LED types still develop heat in their chip. We need to cool it, otherwise the LED will burn out due to overheating. There are two main backlighting types, edge and direct. In the edge backlight unit, there is an optical diffuser plate behind the LCD sheet. This plate is made of opaque plastic that diffuses light uniformly across its whole surface area. The light is sent sideways into the plate by lamps that are tightly connected to the plate's edges. When the plate is lit, you can see a bright shining rectangle. The direct backlight unit has a large field of lamps. The field is as big as the LCD sheet. Each lamp will light a part of the screen in front of it. In the above picture, the lamps can be thin CCFL tubes or LEDs. Here, we are only interested in the LEDs. Later, you will see the LEDs allow us to dim their brightness. This increases the picture quality a lot. This backlight unit contains a field of few thousand LEDs that are mounted behind the LCD panel. Each LED has a small lens to focus its light to the screen. That's why this construction is called Integrated Optical Lens (IOL). The LEDs are grouped in LED blocks. Each LED block will produce light as needed. This construction allows a high brightness with local dimming, but it is difficult to make a very thin TV from it. This backlight construction has been in use for a very long time with CCFL tubes before LEDs were applied. Dimming was not an option then. Here we talk about edge backlighting. The edge solution uses one big diffuser plate that spreads the light uniformly across the screen. The lamps are mounted on the edge of the diffuser plate. This construction is attractive because it can be made very thin. We light the screen uniformly. If we change the brightness, it will be for the screen as a whole. The left-hand side backlight construction has been in use for a long time with CCFL tubes. Dimming was not an option with CCFL tubes. After we started using LEDs, dimming is possible and allows us to dim the brightness per each subsequent frame. We can even go further when we arrange the edge LED in blocks. We can control this block independently. These allows us to vary the backlight brightness locally by dimming certain LEDs. But this dimming happens in more rough manner compared with IOL that has hundreds of fine LED blocks spread behind the screen. The right hand example shows that the LEDs are mounted only on the top edge and bottom edge and make up 12 large dimming blocks. The IOP integrated optical plate combines the best of both, a high quality picture that we can get from local dimming and the thinner construction of the edge backlight unit. Here, the backlight unit is made up of few hundred small diffuser plates called optical plates. Each plate is edge lit by LEDs from only one side. The diffuser plate will spread the LED light uniformly across its areas. Each plate is controlled independently so we can do local dimming. ALEF Advanced Light Emitting Film is the LG unique LED backlight technology that combines the ultra-thin of the sleek edge-lit TVs with the picture quality of full LED slim panels. Nano LED lighting technology is an extremely thin film printed with minute dots positioned in front of full array of LEDs. The film disperses light more evenly and effectively across the screen. On top of this, another film called DBEF, Dual Brightness Enhancement Film, increases the brightness of the LCD screen by recycling most of the light that is normally lost in the rear polarizer. As with the other full LED backlights, the ALEF is divided into large number of equally sized blocks. For example, for 45 inches or 55 inches, total ALEF backlight unit is composed of 240 or 288 controllable local dimming blocks. Local dimming has number of side effects too. One of them is halo effect. What does happen? Some areas are less dark due to crosstalk on certain dark scenes. A good example is the no signal on-screen display message that is displayed when there is no input signal detected. This means that the darkness around the left-hand side of the on-screen display will be less deep than the right edge due to light leaking into adjacent blocks. The intensity of each LED block is calculated from the local average light intensity in the picture content. Here we see that the average intensity for the two blocks at the left-hand side of the on-screen display is higher than the average intensity for the right-hand block. The two left-hand block will thus be lit brighter than the right-hand block. Pixel compensation will greatly reduce this effect. Another side effect of local dimming is white level variation. The difference in backlight intensity may cause also a variation in white level in the on-screen display rectangle itself. Also, the brightness level with the on-screen display rectangle will vary when the on-screen display wanders across the screen. Either 3 blocks or 6 blocks are used in this example. Pixel compensation will greatly reduce this effect. Why do we use pixel compensation? The picture in the top left is the original picture without local backlight dimming. You can clearly see that the dark background looks bluish and is not deep black. The lower left picture shows a deeper black because the backlight has been dim, but now the text "moonlight" is now hardly visible because of black crush. For a better display of text or details in dark area, we need to enhance the brightness of pixel in those area. A way to solve this problem is to use a pixel compensation circuit that adjusts the voltage on the liquid crystals to pass more light in areas where the backlight is dim. In addition, pixel compensation can also be used for removing crosstalk, also known as halo effect, by reducing the brightness of the LEDs at high contrast transitions within an image. Why do we need scanning? Motion blur is an apparent striking of rapidly moving objects in a still image or a sequence of images such as a movie. Blur is major shortcoming of LCD technology in general and is due to three well-known phenomena: slow response time of liquid crystals, scan and hold feature of LCDs, slow pursuit nature of the human visual system, allowing us to see a steady picture even when it is flickering at 25 times per second. Due to the above effects, we will still see overlaps between the frames. This overlaps can be regarded as an unwanted memory effect. In other words, the picture of previous frame has not yet been forgotten when the new frame arrives. The example of the football is exaggerated to show the smearing effect behind a moving object. When the pixel give only short flash of light within each frame, we will see the same peak brightness, but there will be less memory effect. So the previous frame will already be forgotten when the next frame arrives. As a result, we will observe no smearing effect behind a moving object. The physical difference between the CCFL and EEFL is in the electrodes. The voltage between the electrodes creates a plasma that illuminates the internal coating with UV light. The coating becomes activated and sends out visible light that we can see. The EEFL is popular because a number of tubes can simply be electrically driven in a parallel circuit. The biggest advantage of EEFL is that one inverter is able to drive multi-EEFL. The difference between CCFL and EFL operation. The voltage current characteristics of CCFL shows a negative resistance. This implies that tubes cannot be connected in parallel on one inverter. Each tube requires its own inverter. The EEFL has a positive different voltage current characteristics that allows the tube to work in parallel on one power supply. So EEFL has the big advantage of a simple structure since one single inverter can drive all the tube. Also, the manufacturing of EEFL is more simple because the electrodes are applied on the outside skin of the tube instead of internally molten in the glass. The LED has been around for some time now. Decades ago, it became commercially available as a tiny glowing spot of red light, later also green and yellow light. It took some time before we were able to produce also blue LEDs. The light output of the LED has increased drastically, and today there is a trend to replace the traditional lights by white LED lamps such as in spotlights, torches, and in the automotive industry. Because the LED can be switched on and off in an extremely fast manner and has a high light output, it is ideal candidate for application in the backlight for LCD panels. As a white LED does not exist as a chip, we only have red, yellow and green LED chips. For that, we need to create white light by using a trick. The RGB LED solution is based on using three different LED chips for red, green and blue, either combined in one package or as separate LEDs. Red, green and blue light will be mixed to white light then. The RGB LED allows a white color gamut exceeding the NTC standard. Practical figures are 105 to 125% of NTC. The other way for generating white light is using only one blue or ultraviolet LED chip with some extra to it. We will take a look at the working in the next slide. Actually, we start with a blue or ultraviolet LED that is buried in an epoxy mold that contain phosphor. These phosphor will make a color shift. They convert the blue or UV light into another wavelength, green or red light. Please remember that this process with phosphor looks similar to the process in plasma TV where phosphor are used for generating visible light when they are illuminated with UV light. Red, green and blue light emerge together from the top side of the LED, and this will be perceived by the human eye as white light, although often as bit bluish.